Nice. Okay. Go back to present. Right. Mic not muted, video muted. Alright. I know if you're seeing the well, if you're not hearing me, if the presentation now working properly. I know I started back the recording and stuff just now, so things might be a little wacky. Okay, so I hope your head not spinning too much, because that was all one topic. I know it's a giant topic, but that was all one topic. All of that was ACLs. So I just wanted to go through it. Yeah, I just wanted to go through it and try to answer all the questions you might have when you start configuring ACLs, because Cisco did ask us to configure ACLs, right? Even though they put it kind of in between, and it's not much percentage, and it kind of in between security. But I wanted to try and answer all the questions anyway. So read this again if you're still confused, and do the lab on it. The lab will really help. Once you start configuring it, it should start clicking in your head a lot more. And you'll start to memorize the commands as well. So let me know if you're still confused about it after the lab, and after, well, rereading the slides there. So now we're going to go through another kind of heavy topic, right? Configuring layer 2 security features. So to develop a comprehensive security plan for our network, we need to consider security at every layer and consider the entire attack surface of our enterprise. In this section, we will examine some common features that Cisco offers to protect the network at layer 2. One common and simple attack that can be executed at layer 2 is a DHCP attack. Most access environments facing end users rely on their DHCP servers to manage assignments of IP addresses, gateways, and DNS servers, and all of that, right? All of that stuff that we covered when we talked about DHCP. And most access environments rely on that to manage these things for their end users. Nobody wants to tell their end user, hey, pull up this setting and type in this IP address and this subnet mask and this gateway and stuff. A lot of people not very techy, right? So, however, these end devices are not configured for a particular DHCP server. They simply accept whatever DHCP offers they received from whatever DHCP server responds to their DHCP discover message. So remember when we discussed the whole DHCP process, we went through this thing called DORA. And the very first message in that DORA process was DHCP discover, right? So just think of it like you now reach home and you put on your Wi-Fi in your phone. Your phone is going to set out this DHCP discover, which will basically will tell you your modem or your router, hey, I need an IP address. Are there any DHCP servers out there? And there is no authentication or security built into this process. So if, for example, if your neighbor had a DHCP server somehow connected to your network, that server could respond and could say, hey, yeah, your IP address, look on here. And then your modem might just be there, and it could never accept that DHCP discover or request because somebody else responded first. So your client will just accept whatever offer it receives from whichever DHCP server. And this is obviously a huge problem, right? So in a typical environment, you want something like this. One client sending out this DHCP discover, which is a broadcast message, and one DHCP server will respond with an offer. But if you have multiple DHCP servers, then you're not sure exactly what's going to happen there. Now consider this scenario. An attacker is able to connect into this network and submit many fake requests for DHCP leases, thus performing an attack known as a DHCP starvation attack. The attacker is thus able to effectively disable the DHCP server. They are then able to connect their own rogue DHCP server into the network and distribute whatever DHCP parameters they desire. This is commonly used by attackers to sniff traffic and collect credit card details or personal identifiable information, PII. I have personal health information as well, personally identifiable information. There was a word for this. It basically means your name, your email address, your social security number if you're in the States, your mom's maiden name, those kind of things that could be used to perform an attack on you. So basically what we're saying here is the attacker is going to connect into the network and they're going to submit a bunch of DHCP discover messages. So they're going to basically tell the DHCP server, hey, get my IP address, go get my next one, and the next one, and the next one, and just keep going like that until the DHCP server is out, until the whole pool of DHCP IP addresses are assigned. And thus the attacker is able to disable this DHCP server, because the server doesn't have any more addresses to offer anybody. So therefore it's just going to stay quiet, right? So then they could come in and connect their own DHCP server into this network and then distribute whatever they want, whatever parameters they want. So they could, for example, say, I am your gateway, so connect to me and send me all the traffic. And then it will keep passing your traffic to the internet, and maybe it will allow you access to Amazon. And then when you reach Amazon, he's going to collect all your credit card information because that traffic is going through him. So this is what it looks like. So you have your DHCP server here, which you had configured before, but he connected in and he pulled out all the IP addresses here. So he has assignments for all the addresses in this pool. So when you connect in now and you put out that DHCP discover message, he's going to assign you that well, all that information that you need, your IP address, your gateway, your DNS servers, everything, and he'll say, here's your IP. I am your default gateway. So when you want to connect to the internet, you have to go through me because I am your default gateway. Then the default gateway on this guy is going to be a router. So if you want to browse to Amazon, it will seem like it's working, right? You going through his machine, but then again routed through the router here to go out to the internet. So you might think everything is operating normally because you didn't see that your DHCP server is dead. I mean, how many people will know anything about the DHCP server here? So this guy will browse the web like normal, and eventually he will submit some kind of important information that will be useful to this attacker here. So that's why this is such a huge risk. So to prevent against this attack, Cisco offers us a feature called DHCP snooping. With this feature, we designate all ports on a switch as untrusted by default. Untrusted ports are able to submit or transmit DHCP requests, like DHCP discover messages, but they cannot offer DHCP replies, which are DHCP offer messages. So we expect a lot of people on the network to be submitting DHCP requests, right? No problem. But we only expect one or maybe two servers at most to offer DHCP replies or DHCP offers. So we can take advantage of this. And we can say all ports on the switch are now untrusted. You all able to submit requests, but never submit replies. To support genuine DHCP servers in the network, we must explicitly configure ports to be trusted as DHCP servers, thus preventing the attack we saw previously. Only these ports that we designate as trusted can offer addresses to our network. So in this example, we could say this guy here, you have a trusted port, no problem. Everybody else, you untrusted. You all could submit DHCP requests and try to get IP addresses, but you all can't offer IP addresses in return. So we therefore break this chain here. So you see here, we have a DHCP server, DHCP all messages approved, because this is a trusted port. No problem. You could request if you wanted, but really you could offer as much as you want. No problem. Everything else, you are untrusted. So you could submit client messages. So you see you discover MAC addresses, you release and decline, anything associated with DHCP clients, you can submit that. No problem. But if you try to submit something that we expect a DHCP server to submit, then it's going to be rejected by the switch. It's just going to be dropped here because you are untrusted port. So to configure this feature, we first use the IP DHCP snooping command to enable this feature globally. Then we configure IP DHCP snooping VLAN X. So VLAN 1, 2, 3, 4, 5, whatever VLAN we want to enable this feature on. Then on a particular trusted interface that we have connected to our known DHCP server, we use the IP DHCP snooping trust command. We may then use, we may also use the DHCP snooping, the IP DHCP snooping limit rate X on our untrusted interfaces to limit the rates at which DHCP messages can be transmitted to offer additional protection against a starvation attack. So remember, we kinda cut off half the problem here, right? We're saying that if this is a rogue attacker, he could submit requests. He could submit requests here, but he can't submit offers, it breaks the problem of somebody being able to route their traffic through him. But he could still perform a starvation attack, right? He could submit, 100 requests a second, and starve out this DHCP server very quickly. So with this command now, IP DHCP snooping limit rate X, on our untrusted interfaces, we limit the rate at which DHCP messages can be transmitted. So we might say you're only allowed to transmit 2 DHCP related messages per minute. So therefore he could still perform the starvation attack, but it would take a lot longer. So this command will place the interfaces in an error disabled state if it exceeds the rate X. So he would submit 2 requests, and then if he tries to submit 3 in a minute, he would be placed in an error disabled state. So you can see you have trade-offs now, right? Because you might have a case where somebody might be rebooting their PC very quickly, and they might reach the limit of 3 or however much you configure it for, and then their port will get error disabled or shut down. And they're not trying to do a starvation attack. They're trying to do something normal. But this is the price of security, right? You always sacrifice some kind of usability for it. So we just have to know that we configured this thing called the limit rates for IP DHCP snooping. And if we do a show interface, now we see this error disabled, we know we can trace it back to this. So IP DHCP snooping, that's the first thing we put in our config T mode. And this just enables it globally. Then we go int F01 or whatever interface we know is connected to our DHCP server, and we put in IP DHCP snooping trust. So trust this interface, no problem. Exit, and then go interface range, whatever else. So these might be the downstream interfaces that we know a rogue attacker could come in and connect to. And we put IP DHCP snooping limit rate 4. So we limit the rates to 4 messages a second or minutes. I can't remember the exact units. If you put the question mark after here, you'll see the exact limit there. And then exit, and then IP DHCP snooping VLAN, and then whatever VLAN we want. So we could put in multiple VLANs, a range, whatever VLANs we want to enable DHCP snooping on. We can then use the show IP DHCP snooping command to view current snooping settings on the switch. So say we come into the switch here, show IP DHCP snooping. Switch DHCP snooping is enabled. Okay, play. So we know DHCP snooping is on this switch. DHCP snooping is configured on the following VLANs: 999 and 999. And then it's operational on this VLAN because we configured for this VLAN, but we don't have any hosts in this VLAN right now. So it's not actually working on that VLAN. Whenever something connects to this VLAN, then it will become operational there. And you see your layer 3 interfaces, and then different option 82 is a very strange DHCP thing. You have a bunch of other things here, but you see the interfaces there, and then your rate limits if you configure it here, and then trusted or untrusted. There. Okay, whenever that thing disappears, go away. Yeah, so you see your interface there, and it's trusted or untrusted. Now, the second security feature that we are going to examine is called Dynamic ARP Inspection, or DAI. The Address Resolution Protocol, or ARP, allows hosts configured with IP addresses or layer 3 addresses to determine corresponding MAC addresses or layer 2 addresses for other IP addresses that they need to communicate with. This facilitates communications within LANs. So, sorry, Cisco didn't introduce ARP before because it is a very important protocol, and Cisco seems to kind of neglect it all the time. They never put it in to the syllabus explicitly. So we kind of need to wiggle it in different places. So here's how we introduce it, right? So the Address Resolution Protocol, or ARP, basically performs a translation between layer 3 addresses and layer 2 addresses. Remember, DNS performed a translation between host names and IP addresses. So now we're saying ARP performs that translation between the layer 3 and layer 2. So we know about layer 3, which is IP addresses and routing tables and routers and routing protocols and all of that. And we also know about layer 2, which is switches and MAC address tables and spanning tree and all of those things. So the protocol that kind of links both layers together is ARP. ARP will tell you have IP address X, and the MAC address that corresponds to IP address X is this. Or you want to talk to this host, which is IP address 192.168.1.1. Well, to talk to that host, you need to know their MAC address, because that's how you're going to get data to them on the LAN. So to figure out that MAC address, you call ARP and you ask who has the MAC address for this IP address. So you see right here. So this guy here, he has an IP address. This guy also has an IP address here. So he knows he wants to reach this IP address here. So he knows he wants to reach that. So he has a packet destined for this IP address here, but he doesn't know the MAC address associated with that. So what he does is he sends out an ARP request. So you see this ARP request. If you see it in Wireshark, you might see a message like, who has IP address 172.16.2.2? You'll see the request going out there, and then this guy will see it and he'll say, hey, I actually have that IP address. Let me respond there. And you'll see he respond, and you'll see the IP address there, and the MAC address will be in that reply. So this guy will get a response from him, and he'll say, hey, I have that IP address. And here is my MAC address. So then he could populate this table and say, this IP address corresponds to this MAC address. Yeah. This is an extremely important process because hosts rely on these ARP messages to decide where to send their data. For example, a PC in an enterprise LAN uses an ARP message to get the MAC address of its default gateway, which is usually a router in the LAN. However, this process also extends our attack surface. A special ARP message called a gratuitous ARP message can be sent by a host machine without first having received an ARP request. Attackers can exploit this ARP message to force other hosts on a network to send packets to them by spoofing the MAC address of another host in this ARP message. So basically what we say is that you don't have to wait till somebody says, who has this IP address. You could just send it out and say, hey, here's our ARP reply. I know you didn't ask for it, but I'm telling you anyway. Just update the table there. This IP address corresponds to this MAC address. So even though this guy had sent this ARP reply, 5 minutes ago, if somebody comes in now and says, hey, this IP address actually corresponds to this MAC address, and that MAC address is different from what he sent, but this guy doesn't know that. He would just say, oh, okay, thanks for the update. And now any messages that he has for this IP address, he's going to send it to that new MAC address. So it might go to this rogue attacker now instead of going to this router there. Through this thing called a gratuitous ARP message, which is just somebody not asking you for an ARP message, like this. They didn't send that ARP request, but you send them a reply or an ARP update just in case. So you have an ARP reply here, and you see the update here. So he says, hey, this IP address, it was MAC1 before, which was this guy, right? But I just come in now, and I actually want you to send those messages to me. So you see MAC equal MAC A, he's gonna send that. And this router is going to say, oh, I had this MAC address before. Okay, but you send me this this gratuitous ARP now, and you're telling me this IP address is actually corresponding to this MAC address. All right, I'm going to update it, no problem. So now, when this router wants to send messages back to these PCs, he's going to look at his ARP table, and then he's going to say, oh, I have this IP address here. I'm trying to send a packet to this IP address here, but my ARP table says that this IP address corresponds to this MAC address. So the packet is going to come here, go here, and then go down here. It's not going to come here anymore. So you can see how this is dangerous, right? So here you can see we have a man in the middle. So this is what we do here. If we update this MAC address here, and we had MAC1, so MAC1 here, we sent out the ARP already. We went through that whole process already, and we sent who does this IP address and this MAC address correspond to. So before we had the correct thing. We had this IP address here, and we had MAC1. This IP address here, and we had MAC1. But then this guy, this man in the middle now, came, and he sent out that gratuitous ARP message, which said, hey, this IP address, you had that guy before, but you're actually wrong. This is the actual MAC address that corresponds to. So now this router will update its ARP table and send back a response, and it will go to him. And then he's going to process that message and do whatever he wants to, and then he's going to send that on just to make sure that this guy doesn't see anything. So you see 1, 2, 3, 4. So he's going to send out the packet. It's going to go here, and then come back here, go to here, and he's going to send it through. He doesn't want to kill this chain here because he wants PC1 to keep thinking that he has direct connectivity to this router. Just so that he could keep going to Amazon or eBay or whatever Republic Bank or whatever else. So he will get the responses and he will have packets transferred back and forth. It's just that these packets don't go straight to him and come back there. We have this man in the middle now because this router thinks that this IP address corresponds to this MAC address here. So how can we prevent this? So dynamic ARP inspection, which is DAI, leverages tables such as DHCP server bindings or statically configured ARP ACLs with IP and MAC address pairs defined in them. So we have two main sources of tables here, right? We could either use our DHCP server bindings or we could put in an ACL to say this MAC address corresponds to this IP address. And it always will. If somebody comes and tells you this IP address corresponds to this other MAC address, then ignore them. I am telling you that this IP address is supposed to correspond to this MAC address. So using these data pairs with IP and MAC address pairs, that's what we're saying here, IP and MAC address parents, because that's what ARP does. Using these pairs, the AI examines all ARP messages passing through the node and compares the actual ARP request to the mapping that it has in its table. If the address pairs are the same, then the ARP messages are allowed. If they are different, then they are discarded. So if it sees an ARP message and it says, okay, this IP address corresponds to this MAC address, it will check its table and it will say, hey, you know, according to my DHCP server bindings, that's correct. Go on through. Or according to my ACL that somebody configured in me, that is true. Go ahead. But if it sees an ARP request or ARP response, like a gratuitous ARP response, that says, you know, this IP address corresponds to this MAC address, and that doesn't match what it has in its server bindings or its ACL, then it's going to be discarded. So you see here, come in here, origin, that's IP address, origin, MAC A. So you see that IP address, okay, that IP address matches there, no problem. But look, I have MAC 1 and you have MAC A. That's not matching. So this switch is going to say, I had a DHCP snooping binding table from before, so I'm going to use that as a reference. And I saw that this IP address was corresponding to this MAC address, MAC 1. You're telling me that this IP address corresponds to this MAC address. That doesn't match up with what I had in my table. And because I have this nice thing called DAI implemented, then I'm going to drop this packet. So then this will never reach through the switch. And then the router and the PC here are never going to be confused because of this this gratuitous ARP attack. This message will just go here and it will get dropped at this switch right here. So to configure DAI, we first use the command IP ARP inspection VLAN X. We use that command to enable DAI on a particular VLAN X. So you can do VLAN 1, 2, 3, 4, 5, 4000, whatever it is. IP ARP inspection, VLAN, or whatever. Then to configure a port as trusted, for example, a port connected to an upstream router, we use the IP ARP inspection trust command under the interface. So for example, we might not want to perform these inspections on every single interface, right? If we have an interface connected to our upstream router where we know an attacker can't come in because they won't be able to get into our data center, we could put this as a trusted interface so that we don't have to examine any traffic coming in there and we won't be dropping traffic unnecessarily. Remember that DAI is usually paired with DHCP snooping so that the node has a database of IP to MAC address pairings to trust. So usually we're going to put IP ARP inspection or dynamic ARP inspection on the same node that we put DHCP snooping on so that we could use that table that DHCP snooping will build to put, well, to enforce ARP inspection. So you see IP ARP inspection VLAN 11. We also had DHCP snooping on VLAN 11. So we line it up there. Then we have IP DHCP snooping trust on this interface. So we also want to put IP ARP inspection trust on this interface. To verify the operation of the AI, we use the show IP ARP inspection command. So show IP ARP inspection, and we can see if we put in any of these advanced configurations or what VLANs we configured on. So we see we had just configured this on VLAN 11. So we see VLAN 11 showed up here. We see it was enabled for this VLAN and it is active. So clearly we have interfaces active in this. Whether we configure login and DHCP login, and whether we matched any ACLs or any static ACLs. In this case, we expect it to be blank because we're using the DHCP snooping table. So we don't need to configure an ACL to hold this parent. So you see lower down in the command, you'll see your actual number of packets that went through. So you see VLAN 11, we had 11 packets forwarded and 0 dropped. And whether we had any DHCP drops or ACL drops as well. So you see we had 59 forwarded and 0 dropped, so nothing was blank, right? We had no attackers coming into the network. If we see or we expect an attacker to come into the network, or we suspect that somebody's attacking the network with DAI, we will see this dropped counters increasing, and that's how we'll know DAI is doing its work. Or in the case of accidental enforcement, we might have genuine traffic being dropped because of DAI, and we'll see this counter increasing, and we know that nobody's attacking the network. So we'll know we need to disable this IP ARP inspection. Now the last layer 2 security feature that we are going to cover is called port security. So port security allows us to limit the number of MAC addresses that can be learned by an access port in a switch. This prevents users from bringing their own switches into the network. Port security is configured under an interface and can only be configured for an access interface, not a trunk interface. Remember we mentioned access interfaces and trunk interfaces in section 2. Section 1 or section 2? I think it was section 2. So only if a port is an access port can you configure port security on it. So port security restricts port access by certain MAC addresses. Basically, what we're trying to prevent here is if we give you an outlet in the wall and we expect you to plug in a desktop into there, we don't want you bringing your own switch into the network, plugging in a switch there, and then connecting in, a phone and your own laptop, and then your desktop into there, and breaking out that port into more ports. So the first configuration step is to navigate to the interface that we want to protect and enter the command switch port security maximum n. So this limits the number of MAC addresses that a switch can learn on a particular port to n. The default is 1. So if we connect a port directly to somebody's desktop, we might want to leave this default as 1 because we only expect our desktop to be connected there. If they ever connect in a switch, then we're going to have more MAC addresses being flooded and being learned on that switch, right? So this MAC addresses will go up from 1 to 5 or 8, depending on how big the switch is. Most ports will require only 1 MAC address, but there may be exceptions. So for example, if you know about a port going to a phone and a PC behind the phone, you know you're going to need at least 2. You might want to put 2 plus 1 just to be safe, just in case you swap the phone or you disconnect a cable and you put it in an XPC or something like that. You might put it as something a bit higher, but definitely it's not going to be 8 or 10 or 100. So the next configuration step is to either enter the static MAC address that you expect to learn on the interface using the command switch port security MAC address and any MAC address. So you put in that command, or you configure switch port security MAC address sticky. And this command lets the switch learn the MAC address or MAC addresses dynamically as frames are forwarded through the interface. So this is more in line with what we know, right? When you have frames forwarded through a switch, the switch will look at the source MAC address and it will add that to its MAC address table. So in this case, we put in this, we're going to let the switch continue to do that. We're going to say, switch, you continue to do that. You learn your MAC addresses, but I also want you to sticky those MAC addresses. I want you to remember those MAC addresses, and if I put maximum 2, then you're only allowed to learn 2 MAC addresses through this port. The alternative there is to just put in this command, switch port security MAC address, whatever, under the interface, and that will tell the switch, hey, I see you are connected to a desktop with MAC address XXXXXXX. So I want to put in this, and I want you to only allow that desktop to communicate through this port. But this one is a lot more difficult to maintain. Remember, you have to put this in for every single port on every single switch. So you'll usually see this one being used. So we then need to configure the action that we want to occur when an unauthorized MAC address is seen. Cisco offers 3 options: protect, which is to drop all traffic from unauthorized addresses but do not raise any alerts. Then restrict, which is to drop all traffic from unauthorized addresses and raise alerts. And then shut down, which is to block the ports as soon as unauthorized addresses are seen and to generate an alert. And this is the default. So when we say unauthorized addresses here, we mean if you connect a desktop into there and then you see a MAC address from some other address, some strange address that not supposed to be there. So if that happens, Protect will just drop the traffic and that's it. And it'll only drop the traffic from that unauthorized device, right? All the traffic that comes in from the desktop that we expect, that will be unaffected. And then restrict will drop all traffic from that unauthorized address and it will raise an alert so that we know something weird on that port. And then shutdown will block the ports as soon as unauthorized addresses are seen and it will generate an alert. And this one will affect the desktop as well. So the genuine person that was connected there before, the port is now shut down. So they obviously can't transmit any frames through that port as they were doing before. And this is the default. So you need to know how much you want to balance your security and the usability. Because in this case, the person can't use that port again until you fix it. So they will have no connectivity to the rest of the network. If you use the shutdown option, ports go into error disabled state when unauthorized addresses are seen and must be manually reset using the shutdown and the no shutdown command. So shut and press enter and then no shut, and you'll bring it back up and you'll clear that error disable. Obviously, if it gets error disable again immediately, it will go into error disable again, right? So you'll know the source is still there and the reason for the error disable is still there. They can also be re-enabled automatically using the error disable recovery command. By default, this brings it up after 300 seconds. You can also enter the command error disable recovery interval and seconds to change the recovery time. You can also use the error disable recovery cause all or cause a particular cause to ensure that the disabled ports automatically recover from all possible failure cases. So the reason I mention all of these advanced configuration options is that this is hugely disruptive, right? So if you just enable port security on your switch and an unauthorized address is seen on the port is going to become shut down. And by default, if you don't put in any of these advanced commands, that port will just remain shut down. So for example, if you set up a switch at a branch office and then something they do, they move around some cables or something, and the port gets shut down and you are not by that office, that port is just going to stay down until you rechain with a console cable or until you SSH in to shut and no shut the interface. If you put in this error disable recovery command, then it will at least try to bring back up the port after 300 seconds or after the interval that you specify here, which will let them get back on and restore connectivity to them, right? So you'll reduce some of that downtime for them. And you have different causes that you could allow to recover. So you could say, we expect this type of attack, but everything else we could allow the port to recover from. But anytime somebody attacks with this, we want that port to stay down because that is a huge risk to the network. So you see, to verify it, to use show interface and interface name and status, and you'll see a port name here and look at the status there, error disabled. So we know something wrong there already, right? And most of the time, port security is what puts it into its error disabled state. You have other things that could trigger it, but a lot of times, port security is the number one culprit there. So you see show port security and the same interface there. So if you want to verify that port security caused this, you just do show port security and the interface name there. And you see port security is enabled, and then look at the port status there, secure shutdown. So the port was shut down because it saw error cause, a reason to shut down. And if we want to allow it to recover or try to recover after a certain time, we use error disable recovery. Error disable recovery, and then error disable recovery interval, and whatever it is, 300 or 400 or 60 or 30 or however fast you want people to get back on the network. So these are the examples that this switch had for the cause. So you can see it's a bunch of different things, right? We want to say, well, you could put all, which is say enable the timer to recover from all causes. So anything that causes the port to shut down, after 300 seconds, just bring it back up. We're okay. But you could also list out the causes you want. So if you want to say, I don't care about ARP inspection and channel misconfig and DHCP read limit and GBIC invalid and those kind of things, you just list out all of these things. But maybe you want to leave BPDU guard, because if there's something that's causing BPDU guard to trigger, it might be that you have a loop on your network and you don't want to risk that loop causing further damage. You'd rather leave down this one port and break that loop. So you could put everything and leave out BPDU guard, or you could just put all. Once you have decided on your restriction method, use switchport port security violation to configure the mode. So you're going to put switchport port security violation, and then shutdown is the default if you don't put anything. But you could also put protect and restrict, so that you make sure that the port is never shut down. If you have a very important client on a port, for example, you mightn't want that port to ever be shut down, because you'll get a lot more costs for the port being shut down than you would get for saving the network, basically. So you then use the very last thing you do is you put in this command, switchport port security by itself. So you then use the switchport port security command last to actually turn on port security and apply all of these configurations. So all the things we did before was just to kind of tweak port security and let it be configured any way that we want. Whether we wanted to shut down certain ports, or whether we want to put in MAC addresses or learn MAC addresses and all of that. But it won't actually be turned on until we put in this command, switchport port security. Just like the ACL, we could configure all our options, but it won't actually be turned on until we apply it to our interface. This switchport port security lets us turn it on a particular port. So this is what the configuration looks like. So we go int FA01 or F01. Remember, we have to put it as switchport mode access because we can't put port security on a trunk port. And then this is the last thing we want to put, switchport port security by itself. This is what turns on everything. But all the other options, we could put them in wherever. They don't apply to anything until we turn it on with this. So we could put in switchport port security MAC address sticky to say, I want you to learn an address by yourself. And then switchport port security violation protect to say, don't shut down. I want you to allow all traffic from the authorized sticky address, but not allow anything else. And I also don't want it to raise alerts. You see, this one is restrict, so he will raise an alert. And you'll see after it learns an address, it will show up here as well. Now, to verify port security configurations on an interface, use the show port security interface and the interface name command. So show port security interface and the interface name there. Port security enabled, port status secure up. So remember, it was secure shutdown before. So secure up means the port is actually up and forwarding traffic. Violation mode restrict. So we went through the different violation modes, and you know what protect, restrict, and shutdown does now. You have the last source address and then the VLAN. So this is the last MAC address that it saw on this interface, and this is the last VLAN that it was configured on. And then you have that thing called security violation count, which is a counter. So if you see a rogue MAC address and you shut down the port or you restrict the port, whatever action you configured for, this violation count is going to go up. So if you see 0, nothing bad has happened. You only got traffic from the MAC address that you expected. If you see it at 97, okay, we see MAC addresses for something else. So clearly something is triggering these security violations. And that's it. So that was 2 heavy topics. I know it was very, well, yeah, very heavy. But I hope I covered it enough and you understand at least the understanding of them. Any questions about access control lists or DHCP snooping, dynamic ARP inspection, and or port security? Okay, cool. So, well, yeah, if you're confused, either watch the videos or read over the textbook, or just read through the slides again. So I know they're heavy topics. Like as I said, when I first went through these topics, I was real confused too. It's only when you start to use them in your everyday life, then it starts to kind of make some sense. So like when you see a switch shut on a port and you see what what that shutdown command could do, that's when you understand the importance of protect and restrict. But also you understand the importance of putting them on when you have a flood in the network. So it's a bunch of different things you need to manage. Where from my calendar? Right. So today you'll be doing lab 19, which I believe is the last normal lab you'll have. From next week, you'll have lab 20. Lab 20 is not a packet tracer lab. I think I remember that correct. Yeah. Lab 20 is a very custom lab that I designed specifically for this last section here. So I expect a lot of people to have problems with lab 20 because it's not just packet tracer and you follow some instructions and you fire it up. But we'll discuss that next week. Is there a limit of MAC addresses you can set on a port? I actually never checked that. I'm sure there's an upper limit because there must be a number that Cisco could store the variable in, but I'm not sure what the upper limit is. I had to find out. Oh, yeah, it definitely will be higher than 32. It might be like 65,000. But I'll check it out. Yeah, I'll check that out and find the actual upper limit, either in packet tracer or just in Cisco docs. I don't know offhand, honestly. Right, so if that's it, you could go on and try your hand at lab 19, and I'll go on research that, and I'll message in the group. Alright, so till next week, take care.